Hello again everybody. In the last lecture, we talked about how one could use the Schrodinger's equation to solve the hydrogen atom problem. The hydrogen atom is the simplest of all atoms. It has a nucleus of charge plus E and it has an electron of charge minus E. And this particular problem can be handled very nicely using the Schrodinger's equation, and the result of solving that equation are the energy levels such as the 1s, 2s, 2p, 3s and so forth, and associated with each energy level is a wave function which we call as the atomic orbital. Now, in this lecture, what we're going to do is we're going to ask the question as to what happens when we go to other atoms. We're still going to consider initially single atoms, but atoms other than hydrogen, which means that you have more than one electron. After that, we are going to move on to considering molecular systems, systems containing more than one atom. So what we are going to see is that our atomic orbitals, which is what we have when we have single atoms, would get replaced by molecular orbitals. In fact, the atomic orbitals of the individual atoms can be looked upon as getting combined with each other to generate the molecular orbitals of the molecules. Right? So that's really where we are going in this lecture. We're going to introduce the concept of molecular orbitals. First, atoms other than hydrogen. So in the case of hydrogen, we noted that the energy of the energy levels, various energy levels, will have to be minus 13.6 divided by n squared, where n is any positive integer. In the case of atoms other than hydrogen, where the nuclear charge now is Z times E, where E is the charge elementary charge, and Z is of course the atomic number, right? So when we have a nucleus of charge Ze, the allowed hydrogenic energy levels have energies of minus 13.6 Z squared over n squared. Let me explain why we call the spectrum of energy levels as hydrogenic energy levels. For simplicity, we actually assume, initially at least, that the different electrons of our atom do not interact with each other. They do not see each other. Which means that each of our different electrons independently interact with the nucleus and with the nucleus alone. So this assumption leads to a simplification. It basically means that we can go back to our hydrogen atom Schrodinger's equation and simply use the nuclear charge as Ze, where Z is the atomic number, instead of just E. And when we do that, we get the solution ENLM equals minus 13.6 Z squared over n squared. Bear in mind that this result is not correct because we have ignored the fact that electrons interact with each other. And there is another factor also which has been swept under the rug, and this is called screening. We will very shortly visit that. So in any case, now this is our hydrogenic energy level solution, and again N, L and M are our quantum numbers, N being the principal quantum number, and we get this result. What we're going to do now is to use take an example. We're going to take the example of sodium, and we are going to draw the energy level spectrum for that atom. Now I should mention that this hydrogenic energy level route, although it is not entirely correct, it actually provides us an idea of how the energy levels are going to be arranged and how they are going to be filled with electrons and so forth, right? So we will have a spectrum of energy levels, and we are going to occupy each of those energy levels with 2 electrons, right? 2 electrons at a time until we run out of electrons for that particular atom. And that will provide us with the electronic configuration or the electronic structure of that particular atom. So we are going to use sodium as an example, as I just said, and we are going to map out this electronic structure. Sodium has an atomic number of 11, meaning it has got 11 electrons, and the nuclear charge is 11 times E. And what you see here is the electronic structure of sodium. And as you can see, you got the 1s level, then you got the 2s and the 2p levels, px, py, and pz. And note that the 2s and the 2p levels are all degenerate. Here is a new word. Degenerate basically means that the energy levels have the same energy. So the 2s and the 2p levels have the same energy according to this hydrogenic energy level scheme. And then after that, higher in energy are the levels with principal quantum number 3, the 3s, the 3p, and the 3d levels. There is one 3s level, 3p levels, and 5 3d levels. Now, as I said earlier, we start occupying these energy levels with electrons, 2 at a time, and we start with the lowest energy level and work our way upwards, right? So we fill the lowest lying 1s level with 2 electrons, and then we move on to the 2s, 2px, 2py, 2pz levels, fill them all up. So that is 10 electrons, and then we have now 1 electron remaining, and that 1 electron is placed in the 3s level. So this is the electronic structure of sodium. Now what we can do is to actually also write down the value of the energy of these energy levels, right? In the case of, remember, in the case of hydrogen, the lowest level, the 1s level, is at an energy of minus 13.6 eV with respect to vacuum, right? So the vacuum level is assumed to be 0, and the energy of the 1s level in hydrogen is minus 13.6 eV, right? 13.6 eV below the vacuum level. But in the case of sodium, because Z equals 11, the energy values are given by minus 13.6 Z squared over N squared. So using that formula, we can actually write down the energies of the various energy levels with respect to our vacuum level. And we can compare that to experiments and see how well these numbers agree with the experiment. So there it is. So the 1s level is at an energy of minus 1650 eV with respect to the vacuum level, meaning you need to supply that much energy, which is, by the way, a huge amount of energy, to knock out an electron from the 1s level, the core level of sodium, and pull it out to vacuum. Right? Likewise, the 2s, 2p, x, 2p, y, 2p, z levels are at an energy of 412 eV below the vacuum level, and the 3s level is at an energy of 183 eV below the vacuum level. We have merely used the formula up above, minus 13.6 z squared over n squared. What is the experimental situation? I'm just going to write this in blue. So you can see that the experimental values are very different from what we have predicted using the hydrogenic energy level formula, right? And the disagreement becomes worse as we go to higher and higher energy levels. And as I mentioned a little while ago, this disagreement is not too difficult to understand. First of all, we have ignored the interaction between electrons. And the progressive worsening of the agreement as you go to higher and higher energies may be understood in the following manner. Let us consider our 3s electron, the lone 3s electron. Note that this electron is pretty high in energy compared to the 1s and the 2s, 2px, 2py, 2pz electrons, and it's the outermost electron, which means that this 3s electron is probably not seeing the full impact, the full effect of the nuclear charge of 11e, because much of the nuclear charge is probably screened by the core electrons, by the 1s and the 2s, 2px, 2py, 2pz electrons. So it is almost as though our 3s electron is not seeing a nuclear charge of 11e, but something close to just e. The hydrogenic energy level scheme, on the other hand, assumes that our electron, the 3s electron, is seeing the full nuclear charge of Ze, which is why the energy corresponding to that particular energy level is a large number, minus 183 eV, whereas in reality it is minus 5.1 eV. So the key idea here is that screening has been ignored. So does all this mean that we cannot reliably predict the energy levels of anything other than hydrogen? The answer is of course no, although it should be noted that solving the Schrodinger's equation for anything other than hydrogen is non-trivial. It cannot be performed analytically and has to be done numerically in an approximate way. But we can reach any arbitrary level of accuracy that is desired using a numerical route, and that's kind of what is done traditionally. In fact, this has been done for all the elements of the periodic table, and it has led to what are called as the spectroscopic signatures or spectroscopic fingerprints of all the atoms based on the energy level positions and the energy values corresponding to the energy levels. In fact, the spectroscopic fingerprint corresponding to the helium atom was first detected in the solar spectrum before helium was actually discovered on Earth. This is actually the reason why helium got its name, as the Greek word for sun is helios. Let me very briefly point out why it is difficult to solve the Schrodinger's equation for anything other than hydrogen. In fact, why does the solution cease to be analytical? Why do we have to resort to numerical routes to solving the Schrodinger's equation for anything other than hydrogen? The reason is because when you have more than one electron, well, you have a nucleus and then you have more than one electron, let's say, you have a many-body problem. In the case of helium, you already have a three-body problem, and it's a well-known fact in physics that anything other than two-body problems cannot be solved analytically within this context. Nevertheless, despite that limitation, these problems have been solved, as I just noted earlier. And the result of solving the Schrodinger's equation for these atomic problems provides us with what are called as atomic orbitals, which are essentially the wave functions associated with the various allowed energy levels. So we get atomic orbitals by solving the Schrodinger's equation for atoms. With that background, we are going to move on to molecular systems and molecular orbitals. Our first stop here is going to be the H2 plus molecule, which incidentally is the simplest of all molecules. The hydrogen atom is the simplest of all atoms, and the H2 plus molecule is the simplest of all molecules. Why do it contains 2 protons and 1 electron, and is an interesting example of a three-body problem that can be solved exactly analytically by going to ellipsoidal coordinates. Now, this may seem as a contradiction to what I just said a little while ago, that three-body problems in physics within this context are not soluble analytically, and here I am saying that the H2 plus problem, which involves 2 protons and 1 electron, total of 3 bodies, can actually be solved analytically. How is this possible? The trick here is that we solve the problem for the 1 electron for fixed positions of the 2 protons, and we can actually do this, and the justification for this is that the proton is so much heavier than the electron, and so the Schrodinger's equation for the electron and the protons together can actually be factored out. into two separate equations, and one of them purely involves the electron moving in a potential created by two fixed protons, and the solution of the other equation merely gives us the electrostatic interaction between the two protons. And because of this factorization, we are able to handle the electronic degrees of freedom separately in a fixed field potential created by the two protons, and we do it step by step, right? So for every fixed position, pair of positions of the two protons, we can solve the electronic problem, we can get the energy, and we can go from there. And that's kind of what we are going to do right now. And this whole scheme of factoring out a big Schrodinger's equation that involves the dynamics of all the nuclei and all the electrons into more manageable pieces falls under what is known as the Born-Oppenheimer Approximation. And this whole thing is possible simply because the nuclei or the protons are so much heavier than the electrons. In any case, here is our goal for the rest of this lecture. Hydrogen atom problem gives us the atomic orbitals, or AO, and the H2 plus molecular problem is going to give us molecular orbitals, which we are going to call as MO. Let me make myself a little bit of room, and what we are going to do is, before we dive into this problem, I'm just going to make a series of observations. Okay, so let's take a look at this picture over here. So you have your electron here and then the two protons, and let's assume that the two protons are separated by a distance r, and our electron is sitting in the middle. If the electron is sitting over in the middle, we can calculate the force that each of our protons will be experiencing. So there is an attractive force that our proton will experience towards the electron, and then there is a repulsive force that our proton will experience because of the other proton, right? So the attractive force, this force over here, is going to be given by this expression, minus E squared over pi epsilon naught r, where epsilon naught is the permittivity of free space and r is of course the bond length, right? The distance between the two protons. And the repulsive force here is going to be given by this expression, plus E squared over 4 pi epsilon naught r, and you can see that the attractive force is 4 times bigger than the repulsive force. So which is why I'm making the statement over here. So each proton is attracted a lot more to the center by the electron than repelled by the other proton. What does this mean? This basically has the implication that our H2 plus molecule will collapse to a point, because this proton is pulled towards the electron a lot more than pushed away by the other proton, and this other proton is experiencing the same kind of situation. So both the protons should converge onto the electron and collapse to a point. But it is known that H2 plus is a stable molecule, or stable molecular ion, I should say. It does not collapse to a point. It is a stable molecular ion with a specific value of the bond length r. The reason it is possible for our molecular ion to be stable is because the electron is not always at the central position between the two protons, and the electronic position is really governed by the molecular orbital that the electron is going to reside in. So that's going to be our next step. In order to get to the molecular orbital, we need to set up the Schrodinger's equation for our H2 plus problem. So here is our modified picture of our H2 plus system. The two protons, proton 1 and proton 2, are at a distance of r with respect to each other, and this is our electron, and it is a distance of r1 from proton 1 and r2 from proton 2. So that's a general position for our electron, And of course, we are assuming that the two protons are clamped at a distance of r with respect to each other. And as I mentioned earlier, this is what is called as the Born-Oppenheimer approximation. So we're going to set up the Schrodinger's equation for our electron in a potential that is created by these two fixed protons. And here is the Schrodinger's equation. Okay, so we have a big Hamiltonian here, which I'm calling as this H. So this whole thing here is our Hamiltonian operator. This again, remember, is the time independent Schrodinger's equation for this system. Right? The first term in the Hamiltonian here represents the kinetic energy operator. It represents the kinetic energy of our electron. And the second term over here is the potential energy operator, representing the interaction between our electron and the two nuclei, or the two protons. And R1 and R2 are of course these distances. Now I've also introduced another distance R over here because we would like to choose the bond center, the midpoint between the two protons, as our origin, and so our electronic position is represented by R. Right? So our wave function, this is the wave function of our electron, which is a function of its position R, and you have the wave function on the right hand side as well, because remember, the Schrodinger's equation is a eigenvalue problem, and the energy that we seek is this quantity over here. This is the energy of our electron for a fixed bond length R, right? So which is why R is actually tacked on here. So this is the electronic energy, which is actually a function of R. So for each choice of capital R, this equation can be solved, and you will get the energy of the electron for that choice of R. So good. So we have a scheme here to compute the energy of our electron for a fixed position R. But what about the total energy of the system itself, right? What is the total energy of our entire H2 plus molecular ion? So there it is. So this is the total energy of our entire system being the H2 plus molecule, right? So it's the electronic energy EEL, which is this here, which we get from the by solving the Schrodinger's equation. That's just the electronic part of the total energy. But you have the two protons sitting at a distance r with respect to each other. They are repelling each other. So there is an electrostatic energy contribution to the total energy, which will be this quantity over here. So this is the total energy of our molecule itself, you see. So for each choice of capital R, we can solve the Schrodinger's equation, get this quantity, add it to this quantity, and then we get the total energy E. And we can plot this total energy as a function of capital R. We find the minimum, there will be a minimum, and that minimum will correspond to the equilibrium bond length of this molecule. So here is a cartoon that depicts what we expect to find out in the end, right? The total energy E as a function of capital R, the bond length, is going to have this type of a behavior with a minimum, and the minimum energy, and the energy corresponding to the minimum will be the bond energy of this molecule, and the R corresponding to the minimum will of course be the equilibrium bond length. Well, okay, all that is well and good. How are we going to get to our EL, the electronic part of the total energy? So in order to do that, of course, we need to solve the Schrodinger's equation, and we are going to suggest a form for our wave function, psi of R. Now, when the electron is close to one proton, it's going to be somewhat like the hydrogen atom situation, and so the electron will be in the 1s orbital, in a 1s like atomic orbital corresponding to that proton, whereas when the electron is close to the other proton, it is going to be in a 1s like atomic orbital corresponding to that proton. So a reasonable guess for the molecular orbital, for the wave function of this H2 plus problem could be some kind of a linear combination between the two atomic 1s orbital. So there it is. So here is our suggestion for the wave function psi of r of the molecular system, right? So this is our the molecular orbital, the wave function of our molecular system, and we are saying that it is a linear combination of two functions, phi1 and phi2, and c1 and c2 are just scalars. They are just numbers, coefficients of this linear combination. Phi1 of r1 is nothing but the 1s orbital of atom 1. If proton 1 were to exist just with our electron just by itself, that's going to be a hydrogen atom, and this phi1 of r1 is nothing but the 1s orbital of that hydrogen atom. And likewise, phi2 is the 1s orbital of atom 2. So this is going to be our suggestion for the wave function. It turns out that it is a reasonably okay guess to get a qualitative picture of what will happen, and our goal now is to just determine the values of C1 and C2 for the H2 plus problem. So let me make myself a little room. I've just rewritten our Schrodinger's equation for the H2 plus problem in a slightly more compact form. Instead of writing out the entire Hamiltonian, I've just used the symbol H. So H psi equals E psi. So that's our Schrodinger's equation. And there are many ways now to go forward from here. One possible way is to multiply both sides of this equation on the left by phi1 star of R1, and we're going to integrate it over all of space. Okay, so there we have it. We're going to take this equation over here, multiply on the left of both sides by phi1 star R1. The star here, note that the star basically indicates that this is the complex conjugate of phi1. We're going to multiply by phi1 star on both sides and integrate over all of space, right? And that is what I've written down over here. All I've done is I've multiplied on both sides and integrated over all of space. Since this is a 3D problem, it's d cube r. And for simplicity, I've just dropped the r's, r1 over here, r2 over there, and same thing over here, just to save some space. So here is the integral that we get. Let me give myself a little more room, and we are going to just expand out these integrals. So good. So we have expanded it out. So we have these two integrals that pop out of this expression over here, and likewise we have these two integrals that pop out of this expression over there. Now let's make some observations. This quantity here, this integral over here, is equal to 1 because of normalization, right? And this integral over here involves two different functions, right? Phi1, which is centered on proton 1, and phi2 is centered on proton 2. If proton 1 and proton 2 are sufficiently far away from each other, this is essentially the overlap of the two functions, two atomic orbitals. And this integral, as a result, is close to 0. It's approximately equal to 0. It's not quite equal to 0, but it's close to 0. So we're going to make the approximation that this is 0 and throw that away. This is going to be 1. This integral is 1. This integral is approximately 0. So the right hand side simplifies. The left hand side does not really simplify, but we can write them down in a more compact form. So we're going to call this integral as h11, and we're going to call this integral as h12. Okay, so there we have it, the same equation in a more compact form, right? So since we called this as h11 and this as h12 and this is 1 and this is 0, we get the simplified equation, and we're going to call this as equation 1. Now we can actually use this, do the same sort of thing. Let's go back. You see what we did here was we started off with this equation and multiplied on both sides on the left by phi1 star and integrated over all of space. Likewise, we could go back to this equation and multiply both sides on the left by phi 2 star and integrate over all of space. And when we do that, we get a very similar equation, an equation very similar to our equation 1, and which we are going to call as equation 2. So here is what we have. If we go back to our Schrodinger's equation for the H2 plus system, we multiply on the left by phi 2 star and integrate over all of space, we get this set of this equation. And note that the first term here is something that we can call as H21, but because of symmetry between 1 and 2, H21 will be equal to H12, and likewise this quantity here is something we can call as H22, but because proton 1 is equivalent to proton 2, the integral H11 H22 will actually be equal to H11, and by the same argument that we made earlier, this quantity is going to be close to 0 because it involves phi 2 and phi 1, and this integral over here is going to be equal to 1 because of normalization. Okay, so there is our final result. After all of this manipulation, we get this equation here, which you're going to call as equation 2, and just note that equation 2 and equation 1 are different from each other, but they are very similar in form, and for that reason we can combine equations 1 and 2 into a matrix equation. So here is our matrix equation, which is nice and compact, and there is a certain beauty associated with writing our equations in this compact manner. The square matrix that you see over here, that's what is called as the Hamiltonian matrix, right? That's a Hamiltonian matrix, and you see this matrix form is also an eigenvalue problem because you have a matrix, a square matrix over here, interacting or multiplying this column matrix, giving you a scalar, a number, times the same column matrix. So what you saw earlier as the eigenvalue problem is the Schrodinger's equation in differential form, and what you're seeing over here is really the same thing in matrix form. So that's what this is. Now remember, our real goal is to determine the values of C1 and C2. Once again, there are many ways to get to it. The one that we will do is to go back to our equations 1 and 2, and now we have two equations and we have two unknowns, so we should be able to solve for those two quantities C1 and C2. So what we will do is we will take equation 1 multiplied by C2 and subtract it from equation 2 multiplied by C1, and that will basically lead us to C1 and C2. So there we have it, a series of steps leading us to our final solution, which is C1 is equal to plus or minus C2. That's really our solution. How did we get there? Let's just go back a little bit. So here are our two equations, equation 1 and equation 2. We multiplied equation 1 by C2 and equation 2 by C1, and then subtracted these two products, and essentially that took us to this equation over here, and these two terms cancel out, and what we are left with is this equality here, and if this equality were to be true, has to be true, then C1 squared will have to be equal to C2 squared. Why? Because H12 is in general non-zero. We don't expect H12 to be 0. It's an integral, remember, of the Hamiltonian and two-wave functions. So H12 is in general not 0, which means this quantity here has to be 0. And if that quantity has to be 0, we have this equality here, C2 squared equals C1 squared, and which means there are two possible solutions, C1 equals C2 or C1 equals minus C2. So this is our final result. Now we are very quickly going to look at the implications of these two solutions. So let me once again make a little space for myself. So C1 equals plus minus C2 is our general solution. These are our two solutions, and we are going to stick these values into our suggestion for the wave function, and we are going to get two wave functions. Here is one of our solutions. Let me go back for a second to show you our suggestion for the wave function, what we assumed our wave function could be. Look at the first equation up there. Psi of r equals C1 phi1 plus C2 phi2, right? And our goal at that point was to determine C1 and C2. We find that C1 is either equal to C2 or C1 equals minus C2. So we substitute the first solution, C1 equals C2, into this equation over here up top, right? So if C1 equals C2, so we can replace C2 by C1, right? So then our solution for the wave function is going to be C1 phi1 plus C1 phi2. So C1 can be pulled out, and we want our wave function to be normalized, and when we impose the constraint of normalization, we get C1 should be equal to 1 over square root of 2, and that basically took us to this solution over here. So we are substituting one of our solutions, C1 equals C2, into our wave function, and then we normalize the wave function, and we get C1, and C1 has to be equal to 1 over square root of 2, and that is why we get this as our solution for the wave function. Now I've included an index B over here. You may be wondering why B and why not A or something else. Actually, there is a reason. B here stands for bonding. It turns out that this wave function represents a bonding situation, and we will see that very quickly, very soon. So B represents bonding. Likewise, we can substitute our second solution, C1 equals minus C2, into our wave function. And once again we go through this exercise of normalization, and normalization will once again lead us to our coefficients being 1 over square root of 2 and minus 1 over square root of 2, and our final solution for the wave function itself is going to be something like this. Now the second solution has an index A, right? Has an index A. Why? Because it is going to be what we call as the anti-bonding orbital. So we have two solutions, C1 equals plus C2, C1 equals minus C2, and each of those solutions will lead us to either psi B or psi A. So if you use C1 equals C2, you get psi B. If you use C1 equals minus C2, you get psi A. These two quantities here, these are our molecular orbitals. They are the linear combination of our atomic orbitals, and they have both been normalized, and these two orbitals have special features, which is why we have tacked on these indices B and A, B standing for bonding, A standing for anti-bonding. Now let us also make a little plot of how these two functions will look like, and that will allow us to understand why we call them as bonding and anti-bonding. Okay, so let's take a look at this picture I've just drawn. What I've plotted is essentially psi as a function of r. The plot I've drawn here is psi b of r, the bonding orbital, the first equation up top in this slide. Because it's the sum of the two atomic orbitals, you're going to have two positive peaks, right? So if you just had one atom, hydrogen atom, its wave function is going to look like that. Remember, the proton is sitting over here at this location, and the other proton is sitting over here. So the distance between this one and that one is capital R. So if you had just this proton, then its 1s orbital is going to look something like that. If you had just that proton, its 1s orbital is going to look like that. Now since you have both protons, we have this as the solution. It's a phi1 plus phi2, so you get this type of orbital. Note that at the bond center, this is the bond center, at bond center there is a non-zero value of the wave function, right? It's non-zero, which means there is a fair amount of electron density at the bond center, which is what glues the two protons together, and for this reason this is called as the bonding orbital. How does this quantity look, right? Let's make a plot of that in the same graph. So there it is. So the blue curve now is the anti-bonding orbital. So this function has been plotted. Now because you have this negative sign over here, phi 2 is has a negative value, right? It has a negative value, and because you're adding phi 1 and minus phi 2, you're going through a node over here, which means this particular orbital ensures that there is zero electron density, zero electron probability of finding electrons at the bond center, which means it depletes electrons from the bond center. Because you see, if you had just one proton, one hydrogen atom, its wave function is going to look like that with a non-zero value at that position. But the anti-bonding orbital ensures that the wave function goes through a node, goes through zero over there, so it depletes the system of electrons at the bond center. This is going to destabilize our H2 plus system. Imagine if you have the two protons with no electron in the middle. The two protons are going to repel each other. So it's going to be an anti-bonding behavior. So, and for that reason, this wave function is called the anti-bonding orbital. Okay, so now we understand why we call these two solutions for the wave function, the two molecular orbitals, as bonding and anti-bonding. One of them was bonding, the other was anti-bonding. We now understand physically why we chose that nomenclature. What is the next step? The next step is very simply evaluating the energy. So now we have the wave functions. We know the values of C1 and C2 for the two solutions, the bonding and the anti-bonding solutions. We can use that information now to compute the electronic energy. Remember, our goal was to determine the total energy of the system via the computation of the electronic energy. So that's really our next step. Okay, so let us consider our first solution, right? The solution for the bonding situation, the bonding orbital. For which case we have C1 equals C2, which is equal to 1 over square root of 2 because of normalization, of course. We can now stick in the values of C1 and C2 into our equation 1. Let us go back and remind ourselves what our equation 1 looked like, right? Let's go back. So there is our equation 1 at the top of the slide. So we can go back to this equation and stick in values of 1 over square root of 2 for C1 and C2. That will give us our electronic energy corresponding to the bonding orbital, right? Because we have two wave functions, we will have two energies, two EL. The first one is of course the bonding one, right? So that's what we are after first. And then soon after that, we're going to go to our the second solution and substitute that in the appropriate equation, and we will get the expression for the energy of the corresponding to the anti-bonding orbital, right? So let's go back to our equation over here. So this solution that you see over here is the energy of our electron if it was sitting in our bonding orbital. It's H11 plus H12. So there it is. So if you now use the corresponding solution for the anti-bonding orbital, you will get this expression for EL. And note that for the EEL, I have tacked on the indices B and A. B corresponding to bonding and A corresponding to anti-bonding. So basically what this is telling us is, if our electron is sitting in our bonding orbital, then its energy would be this, and likewise if the electron was sitting in the anti-bonding orbital, its energy would be that. Now, and here is another piece of useful information. It turns out that because of the integral involved in the computation of H12 turns out to be a negative number. So what does this mean? It basically means that our EELB is going to be less than H11 because H12 is negative. And likewise, this quantity over here, EELA, is going to be higher than H11 because H12 is, of course, again negative. So because H12 is a negative quantity, we have this relationship here. The uh, the energy of the electron in the bonding orbital is going to be less than H11, which is going to be less than the energy of the electron in the anti-bonding orbital. And because of this scenario, we can draw our electronic structure of our molecular problem in this manner. Okay, so here is our picture of the electronic structure of our H2 plus molecular ion. It's somewhat of a simple picture, but then there is a lot of pieces of information over here. Let's very briefly walk through them. So what I've really drawn are the energy levels ELB and EELA, right? So this is the energy EELB over here, and you know, this is the energy H11, and that's the energy EELA, right? So bonding and anti-bonding. Now here is another thing I want you to note, and that is H11 is nothing but the energy of the 1s orbital. So remember, H11 was just the integral of the phi1 times the Hamiltonian times phi1 again, integrated over all of space. So that should straight away give us the energy of the 1s level of hydrogen atom, which is why I've tacked on this this symbol over here, 1s, and that's phi1, right? That corresponds to our atomic orbital phi1 AO, or atomic orbital phi1. Likewise, on this side you have phi2, whose energy of course is also equal to H11, and that's the 1s level of the hydrogen atom sitting at site 2, atomic orbital again. These two orbitals combine, creating the wave function corresponding to a bonding combination, which is and whose energy is given by that, right? And then the anti-bonding combination has the energy that. Now here is another new piece of notation. See, atomic orbitals are labeled as 1s, 2s, 2p, and so forth. Molecular orbitals are given the symbols sigma, pi, delta, and so forth. Now these two atomic orbitals that have combined, this one and that one, create a bonding combination, which is the molecular orbital indicated as 1 sigma 1s, and the anti-bonding combination, which is represented as 1 sigma 1s star. Star indicates that it is anti-bonding in this particular context. So this is the electronic structure. So if you had a single hydrogen atom, this level is going to be occupied by one electron. Likewise, if you had another single hydrogen atom on the other side, side 2, you have a single electron occupying that. Now you have a H2 plus system whose electronic levels are these. So you have to start occupying them from the lower level, which means you will occupy this level over here. So that level over here will contain one electron. So here I have also shown another way of visualizing the molecular orbitals. Here is the bonding molecular orbital, which is psi b of r, and here is the anti-bonding orbital psi a of r. In the previous slide I showed one way of visualizing these two wave functions, these two molecular orbitals. Here is yet another way. Essentially, you can see that in this particular case, the electron density is distributed around the two protons such that it kind of keeps them together. Whereas over here you have a node. There is a nodal plane. There is no electron density in this region, which is what keeps them separate, which is why it's called the anti-bonding orbital. Okay, so in the final step, we are now going to picture how are the energies of the bonding and the anti-bonding orbitals is expected to vary with respect to the distance r, the bond distance r, right? Remember, this was our original goal, to write down or to determine the dependence of the total energy with respect to r. But before we get to the total energy, why don't we picture how the electronic energy EEL is going to behave with respect to R. So here is what happens. So if you look at this plot over here, what's plotted is the EEL, the electronic part of the total energy, as a function of the bond distance r, the distance between the two protons. It turns out that when C1 equals C2, we have the bonding situation. For that solution, our EEL is going to start from a value that is lower than H11 and then approach the value H11 for very large values of R. Conversely, the anti-bonding solution is going to start from a higher value compared to H11, and then it's going to approach H11 as you go to large values of R. In order to understand why this is happening, we should go back and take a look at the expressions for the two energies, right? So we wrote this down a little bit over here, right here. So here is our expression for the bonding situation, and here is our expression for the anti-bonding situation. In this case, it's H11 plus H12. Here it's H11 minus H12. What I'm arguing is that as R becomes large, H12 tends to 0. And so these two pieces just drop out, and both the solutions, the bonding and the anti-bonding solutions, will converge to H11. That's what is pictured over here, right? And here is the mathematical argument for that. H12 is nothing but this integral, and if R is very large, it means that the location of 1 is very far away from the location of 2, so the overlap between these two orbitals is going to be so big that that you're going to get a 0 for this integral, and so at large values of R, H12 tends to 0. If H12 tends to 0 at large values of R, the two values of the energy, electronic energy for the bonding and the anti-bonding situations, will both tend to H11. That's what is happening over here. Now, this is just the electronic part, right? Now, if we go way back in this lecture, you will actually see that the total energy of our system is the sum of the electronic part. This is the total energy. The sum of the electronic part, which we got from solving the Schrodinger's equation, and the electrostatic contribution, the repulsion between the two protons, the two nuclei. So now we take the plot we just drew for just this piece over here, and to each of the two lines that we got for the bonding and the anti-bonding cases, we add this quantity over there, and let's see what happens. Okay, so here is what we get. Here is our final result, right? So we took the EL curves, these two curves, and added to these two curves the electrostatic contribution due to the repulsion between the two protons, right? Which is a positive number. So you take this curve over here, let's say, and then you add a positive number to it. You're going to make it more positive, so you get that. On the other hand, when you take this curve, which is negative, with respect to H11, of course, now you add a positive quantity to that. It turns out that the positive quantity that you are adding is very big at small values of R, but then it diminishes for larger values of R. So what you get, the net result of adding the electrostatic repulsion to this curve, is essentially this behavior over here, and it will have a minimum. And of course, this energy that corresponds to the difference between the minimum here and H11 is the bond energy, and the radius, the R that corresponds to the minimum, is the bond length. It turns out that if this whole scheme, this molecular orbital scheme, were adopted, and suitable approximations are made, and the integrals are evaluated to a reasonable level of accuracy and so forth, the correct values of the bond length and the bond energy can be predicted. So Schrodinger came up with the Schrodinger equation and demonstrated that that equation can be used to very satisfactorily solve the hydrogen atom problem. He was able to show that the energy level, the electronic structure of the hydrogen atom that you would get is in remarkable agreement with experimental information, spectroscopic information. And subsequently, the community has taken that significantly further to address problems involving atoms with more than one electron, and also molecules involving more than one atom, using the molecular orbital extension to the original Schrödinger theory. The next step that we are going to adopt is to continue further, look at other more complicated molecules, and then eventually we are going to get to solids. So in the next lecture, we are going to start from where we left off here. We are going to plug along and consider a few more molecules, and then we will enter the solid state arena.